Hey guys, welcome back. So, we're going to continue on our lecture series from chapter 5, and we are moving on to section 5.4. In the last two videos, we actually did sections 5.2 and 5.3 together, called that one big thing, and that's what we did last time. And there, we discussed the area under the curve, and specifically how to approximate the area under the curve. In this section, we're going to go over something called the Fundamental Theorem of Calculus. This is probably one of the most important things, if not the most important thing, you should take away from this class. So, I've gone on this tangent a couple times, but I want to re-clarify something. If something is a proposition or a theorem, it is important. If you have a proposition or theorem that is really important, then it is named after a person, specifically, usually the person that either made it famous or the one who discovered it. Now, if you have a theorem that is named, such as the intermediate value theorem or something like that, then it is ridiculously important. They deemed it to be so important that they felt no one person should get the credit, that it is so important that we just have to give it its own name. Now let's look at this one. This is called the Fundamental Theorem. They felt that this was so important that they call this the Fundamental Theorem. If that doesn't scream how important this theorem is, I just don't know what does. But let's take a dive in and figure out what this Fundamental Theorem is. First, recall from the last section where we talked about the definite integral. We defined the definite integral to be the integral from a to b of f of x dx to be the limit as n goes to infinity of the summation of j is equal 1 to n of f of xj star times delta xj, where this summation right here is just the Riemann sum. Basically, we take n number of rectangles of some specified width, calculate the area, sum it up, and we get an approximation. The definite integral is when we take the number of rectangles and we get more and more and more, where we take the limit as n goes to infinity of the number of rectangles. So an infinite number of rectangles of infinitesimally small width. So another way to put it, the definite integral is an infinite limit of a sum of infinitesimally small things. We are talking rectangles that are thinner than a line that you draw with a pencil on a piece of paper. Infinitesimally small, where they are virtually a point wide. Now think about what that means. A point wide. A point is smaller than an atom. A point is so small we cannot conceive how small a single point is. And that's how wide we are talking these rectangles are. The width of the rectangle is virtually zero, but it's not actually equal to zero. So it does contain some area. While the width may be very close to zero, it's not equal to zero. And we take an infinite number of them and we shove them under a curve, we add up the area, and then we get an approximation to the area under the curve. In fact, if we do that, we actually get the area under the curve by taking these infinitesimally small rectangles and we put them one after the other under a curve. We get the area under the curve. We get the exact area under the curve. But there's a small problem. We can only approximate that. We can only come up with a finite number of rectangles. How do you calculate the area of an infinite number of rectangles? That's insane. How on earth are we going to calculate this? Enter what we call the great miracle of calculus. Now, it's called one of the great miracles of calculus, but I would like to say that this is the great miracle of calculus. This is the thing that ties it all together. And we call it the Fundamental Theorem of Calculus. This is one of those things that is just kind of mind-blowing about calculus. What makes it so valuable, what makes it so important, what makes it useful. The Fundamental Theorem of Calculus is going to give that to us. So, lo and behold, let's introduce this fundamental theorem. All right. It's so important, it actually comes in two parts. We're going to start with part one. Duh. If f is a continuous function on the interval ab, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where f is an antiderivative for f. And recall, capital F is an antiderivative for little f if the derivative of capital F is equal to f. That's section 5.1 material. Now just stop and think about this for a minute. Just think. Forget about calculations, forget about homework, forget about everything right now. Just think about this for a second. This definite integral, it looks like this. It is an infinite limit of a summation of areas of tiny rectangles. That's what this is. It's the area under the curve. It is this infinite limit. And when you calculate it, what it turns out to be is the antiderivative of your function evaluated at one endpoint minus the antiderivative of your function at the other endpoint. That's it. That's it. I mean, this is the area under the curve. We do not have to calculate that infinite limit. We do not have to look at that series and see if it converges. We do not have to calculate that. We do not have to evaluate that limit. What the fundamental theorem of calculus gives us is that the definite integral of a function on an interval, or the area under the curve of a function on the interval, is simply its antiderivative, evaluate the endpoints, and you take the difference. That's it. That infinite limit, that limit as n goes to infinity of the summation of j is equal 1 to n of f of xj star times delta xj, it's just equal to capital F of b minus capital F of a. Not only do we have a way to calculate that limit now, we have an easy way to calculate that limit. Just think about that. The antiderivative, undoing a derivative, evaluating it at two endpoints, gives you the limit of the Riemann sums. It gives you the area under that curve. Just think about how strange that lines up. How the relationship between the antiderivative, undoing a derivative, is directly correlated to the area under the curve. Directly correlated to it. It's just that antiderivative, evaluate the two endpoints, take the difference, and you have your area. That's it. That's all you have to do to calculate that gross looking limit. That's it. Doesn't give you an approximation of the area under the curve. It is the area under the curve. That's what makes this fundamental. That's what makes this extraordinary. Because there are a laundry list of reasons we like to evaluate definite integrals in real life. In physics, biology, chemistry, engineering, any science you can think of. I promise you calculus shows up in one form or the other. Any kind of STEM field uses integrals. They use area under the curve. You're summing things up. It's where the notation comes from, this elongated S. Remember, this elongated S from A to B is the limit of a sum. So essentially, the integral is a summation. That's why we use an elongated S. It's just another sum. That's it. And if you think back to limits, those things we talked about approach, how a function behaves as we get closer and closer to a point, but we never actually get there. And we thought, this is kind of ridiculous. Why do we remotely care about limits? But then it turns out the derivative was not only related to the limit, the derivative is defined in terms of a limit. We have that again here. The integral can't be written as a limit. It is a limit. The definite integral is defined to be an infinite limit. It's not like it magically fell out that way. It's not how we went, ooh, these two have to be equal. No, we defined the definite integral to be a limit. Limits are everywhere. Every single time you take a derivative, every single time you take an integral, you're actually doing a limit. Everything else is just techniques to do it. You're always doing limits. And even in the fundamental theorem of calculus, just think about this for a second. That limit of that summation, so you take those Riemann sums, the areas of or the areas of those rectangles, make them infinitesimally small, and you cram an infinite number of them under that curve, add them up, and you get your area under the curve, and you get just the difference of the antiderivative of the function evaluated at the endpoints. That is the fundamental theorem of calculus. That's it. That's what it's saying. If you don't find that utterly remarkable, then we've got to work on your imagination, because that right there, that's cool. Like, that is cool. All right. Well, that's enough of me ranting about that. Let's see how we can apply the fundamental theorem of calculus to find some areas under some curves. Let's start off with this example. We want to evaluate the integral from 0 to 2 of x squared plus 3 dx. Well, to do this, first up, we need to find the antiderivative. So forget about endpoints right now, forget about limits, forget about sums. We just need an antiderivative. So that's what we're going to calculate first. So the indefinite integral of x squared plus 3, well, that's equal to x cubed over 3 plus 3x plus c. Well, that's equal to our capital F of x. This is our antiderivative, where c is some constant. Remember, we do not know what c is, but we're going to show in a minute it doesn't matter what c is in this case. So just bear with me. This antiderivative is equal to x cubed over 3 plus 3x plus c. If you don't believe me, go through the steps carefully. Do the power rule. You'll get the same result. So this is our antiderivative. But now we need to evaluate the antiderivative at the endpoints. We need to find f of b and f of a. But in this case, a and b are 0 and 2. So we need to evaluate f at 2 and 0. This is what we get. F of 2 is equal to 2 cubed divided by 3 plus 3 times 2 plus c. Well, that's just equal to 8 thirds plus 6 plus c. And that's equal to 26 thirds plus c. All right, that's f of 2. Now we need f of 0. F of 0 is 0 cubed divided by 3 plus 3 times 0 plus c. So f of 0 is 0 plus c, where c is that integrating constant. We have no clue what c is. But it does not matter. You'll see in a second why not. Now, the third step. Invoke the fundamental theorem of calculus. Recall that the integral from 0 to 2 of x squared plus 3 dx is simply the antiderivative of f evaluated at 2 minus the antiderivative of f evaluated at 0. We already calculated f of 2 and f of 0. Now we just take their difference. So we get 26 thirds plus c minus 0 minus c. Now this is why I'm saying that the c does not matter. We now have a plus that c and a minus that c. They're going to cancel each other out, and we get 26 thirds. So the integral from 0 to 2 of x squared plus 3 is equal to 26 thirds. This is the area under the curve of this function on this interval. And instead of having to try and figure out how to calculate the limit as n goes to infinity of the Riemann sums, all we did was invoke the fundamental theorem, calculate the antiderivative, plug it at the endpoints, take the difference, and we get our answer. And in this case, that is 26 thirds. But that seems to still be quite a bit of work. We have to go through these 3 steps and everything. There's actually conciser notation we can actually use to calculate this. So let's look at that now. Let's evaluate this integral, 0 to 1 of x cubed plus 2x dx. Well, for the first step, we need to find the antiderivative. Now you just apply the power rule to both these terms, and you'll get this. 1/4 x to the 4th plus x squared. 1/4 x to the 4th plus x squared is an antiderivative of the function x cubed plus 2x. Notice there is no houseboat. There is no constant. Because when we evaluate the fundamental theorem, the constant is just going to disappear. So in this context, we do not care about it. If we are finding an antiderivative, we have to care about it. But when we're evaluating a definite integral, we do not need to worry about the integrating constant. Now notice this bar I have right here from 0 to 1. What that's telling us is that we've evaluated an antiderivative, but we haven't invoked the fundamental theorem yet. It's still telling us we still have to plug in the endpoints and take the difference, which is what we're going to do. This right here, this 1/4 x to the 4th plus x squared, that's my capital F. And we need to get capital F of 1 minus capital F of 0, or f of 1 minus f of 0. So into this function I plugged in 1, into this function I plugged in 0. Now we take their difference. So from here we get 1/4 plus 1, but notice this is just going to go to 0. We have something times 0 plus something times 0. That's just 0. So we get this is equal to 1/4 plus 1, which is just equal to 5/4. This problem should ring a bell. In the second part of the last video, so section 5.2, we actually approximated this integral from 0 to 1 of x cubed plus 2x using, if I'm not mistaken, 5 rectangles and left endpoints. And we actually got a pretty good calculation. But on that slide, I actually gave you the actual value of 1.25. This is how I got the actual area under the curve. 1.25 is just 5/4. So this is better than an approximation. This gives us the exact area under the curve. That's what makes this so important. Now, let's see another example. Because if I said before, and I'll say it again, the only way to get good at this stuff is practice. Now, let's evaluate the integral from negative pi over 2 to pi over 2 of cosine x dx. Analytically, what this is saying is given the function cosine of x on the interval negative pi over 2 to pi over 2, what is the area under the curve? That is what this is asking. Let's do this using the fundamental theorem. So, the integral from negative pi over 2 to pi over 2 of cosine of x dx. First, we need to find the antiderivative. And if you remember from section 5.1, the antiderivative of cosine is just sine of x. And then the fundamental theorem of calculus, we have to evaluate it negative pi over 2 to pi over 2. And then we plug it in. So the integral of from negative pi over 2 to pi over 2 of cosine of x dx is equal to sine of pi over 2 minus sine of negative pi over 2. This is just implementing the fundamental theorem of calculus. All right, now we're going to use some properties of sine to actually calculate this. You can use the unit circle. That'll get the job done too. But I've got another way we can tackle this. Remember, sine is an odd function. Since it is an odd function, any negative that's inside the parentheses, I can pull out in front. So this is actually equal to sine of pi over 2 plus sine of pi over 2. Just comes from the fact that sine is an odd function. So we get 2 sine of pi over 2. But what is sine of pi over 2? It's just 1. So we get 2 times 1, which is equal to 2. This is just, I think, utterly remarkable. We're talking about an interval of negative pi over 2 to pi over 2. Seriously, it's pi divided by 2. We have an irrational number, a famous irrational number. We divided it by 2, made it negative, called that the left endpoint. Did the same thing with the right endpoint. So we have these irrational numbers as the endpoints of our interval. We have this trig function, and we want to find the area under this curve. We implement the fundamental theorem of calculus, so essentially evaluating an infinite limit of some Riemann sums, and the answer is 2. Just think about that for a second. Irrational numbers, infinite sums of Riemann, or infinite limits of Riemann sums of infinitely number of rectangles, infinitesimal width, and we get 2. This is one of the examples why math can get weird. All right, so that is the fundamental theorem of calculus part 1. Now we want to talk about part 2. Makes sense. We broke it up into 2 parts. Makes sense that we want to talk about both parts. Otherwise, this would just be weird. All right, part 2 it is. Same setup as last time. Let f be continuous on a to b. Now, I didn't harp on this as much as I should have when I just did part 1, but I like to point this out. f must be continuous. F must be continuous on the interval. That is what makes this work. Remember that whole continuity thing we did in chapter 2 that I said was going to be pretty important later down the road? Voila. We require continuity. We require f to be continuous to do all of this. If f is not continuous, we have some problems. We have some workarounds for it, but right now, it's just a big headache. All right, so for both parts, we require f to be continuous. That is incredibly important for this. Continuity is a lifesaver. We love continuity. So, if f is continuous on a to b, then the derivative with respect to x of the integral from a to x of f of t dt is simply f of x, where x is in the interval a to b. So let's think about this. We have a definite integral, but one of the endpoints is a variable, and we are trying to integrate another function f of t. Notice the difference in variables. If it was f of x, this would get really ugly. If you try to evaluate the integral from a to x of f of x dx, you're going to have a hard time. So we're just going to call it t. So the derivative with respect to x of the definite integral from a to x of f of t dt is simply f of x. Just think about this for a second. What it's saying is, if you evaluate the antiderivative and you take the derivative of it at x, you end up exactly where you started with f of x. Now, once again, on these proof things, I like to only do proofs in calculus when I believe that they're going to be constructive. I think the proof of this part of the fundamental theorem actually sheds a lot of light onto what this theorem is saying. So this is a rough proof. I cannot emphasize that enough. This is a rough proof. The real proof takes pages. Mine's going to take, what does it look like? 4 lines? 3 lines? Something like that. So let's evaluate this derivative. So we have the derivative with respect to x of the integral from a to x of f of t dt. Well, first, let's evaluate that definite integral. From the Fundamental Theorem of Calculus Part 1, we get this is the derivative of capital F of x minus f of a. X is the left endpoint, a is the right endpoint. The Fundamental Theorem says we find the antiderivative of f, plug in the endpoints, take the difference, and voila, we have the definite integral. In the next step, we need to evaluate the derivative of this integral. So we have the derivative with respect to x of f of x minus f of a. By properties of derivatives, we can pass it through to each term. So this is equal to the derivative with respect to f of x minus the derivative with respect to x of f of a. Now here's where things get fun. What is capital F of x? It is the antiderivative to lowercase f. So if we take the derivative of the antiderivative, we just end up with f of x. Now you might be asking, what happened to that capital F of a? Remember, a is a constant. X is a variable in this context. A is a constant. So you have a function evaluated at a constant. It's going to be a constant. So the derivative of a constant is 0, giving us the derivative of capital F of a to be 0. So the derivative of this integral is simply f of x. It's showing a relationship to some degree how integrals and derivatives are inverses of each other. Think about that. Derivatives and integrals behave like inverses of each other. They undo each other. That's what's important about this theorem. Integrals and the derivatives, they undo each other given these circumstances. It's not an actual inverse, not like the formal one where we defined a formal inverse, but they behave like it. These actions undo each other. So part 1 gives us a way to evaluate the area under the curve, and part 2 explains the relationship between the derivative and the integral. They undo each other. That's why I think this proof is constructive. It shows how these two can undo each other. If you think about it as integral is going up and derivative is going down, you kind of got an alley-oop kind of thing here. The integral throws that function up, and the derivative slams it right back down. That's what the Fundamental Theorem Part 2 is giving us. But I don't see a couple examples of this. Take the derivative with respect to x of the integral from 2 to x of t squared minus 4t dt. This might look really hard to calculate, having to calculate some antiderivatives, evaluate some endpoints, take the difference, but we don't have to do that. The Fundamental Theorem of Calculus Part 2 says that the derivative of this integral is simply x squared minus 4x. Yeah, that's it. The Fundamental Theorem of Calculus is really just highlighting the relationship between the derivative and the integral. Now let's see another example. Let's take the derivative with respect to x of the integral from 3 to x of secant squared of u du. Now we look at this. This might get weird. Is it going to be tangent? Is it going to be some sort of secant tangent? No. The Fundamental Theorem of Calculus Part 2 tells us that the derivative of this integral is simply secant squared of x. Once again, the Fundamental Theorem of Calculus Part 2 is merely expressing the relationship between the derivative and the integral. That to some degree, they just undo each other. All right? So that's part 1 and part 2 of the Fundamental Theorem of Calculus. But now we want to use the fundamental theorems to come up with some additional rules. So in section 5.1, we had some rules with derivatives involving pulling out constants. The integral of the sum is the sum of the integrals. The integral of the difference is the difference of the integrals. Now let's introduce some more. First up to bat, we have if we have one function f of x is less than or equal to another function g of x, then the integral from a to b of f of x dx is less than or equal to the integral from a to b of g of x dx. Okay, let's think about what that's saying. Remember what the definite integral is on an interval. It is the area under the curve, where f of x is essentially your height, where between all the numbers between a and b, you're plugging into f to get the height of your rectangle. Dx denotes your change in x, or your width of your rectangle. And so you're calculating up the entire area of this function on a to b. But since f of x is less than or equal to g of x, what this is saying is that the area under the curve of g of x is actually bigger than the area under the curve of f of x. Think about that graphically. If you have one function that's above the other function all the time, then the area under that second curve is going to be bigger than the area under the first curve. Or if one function is bigger than the other function, then when you take this integral, the inequality remains the same. So essentially, when you have this inequality, you can integrate over both sides and the inequality remains the same. Now, the next one. Excuse me. If we have the integral from a to b of f of x dx plus the integral from b to c of f of x dx, well, that is simply the integral from a to c of f of x dx. What this is saying is we can split up the integral into different segments. If we have an integral from a to b of f of x on 1, but then the second integral starts at b and goes to c, we can combine the integrals to just be the farthest left endpoint to the farthest right endpoint. It's a way of combining these integrals. Now, so the next one. The integral from a to b of f of x dx is equal to negative integral from b to a of f of x dx. What this is saying is if you have these limits of integration and you want to flip them, all you have to do is put a negative out in front. By putting a negative out in front, this will allow you to swap the limits of integration. One more. The integral from a to a of f of x dx is equal to 0. So our left endpoint is a, our right endpoint is a, and we're trying to evaluate this integral. Think about what an interval from a to a is. It's just the point a. So this is essentially asking us, what is the area under the curve of a function at a point? Well, this is saying it's equal to 0. Think about that for a second. I find that remarkable. So the area under the curve of a function at a point is equal to 0. But if we do that for the entire interval and we add it up, we don't necessarily get 0. We can get a positive number. We can get the actual area. So this is why limits are so remarkable. we are taking things that are virtually zero and adding them up and getting something that's not zero, because they are tending to zero, but they're not actually equal to zero. So that's just a fun thing for you to think about. Now, these last three, what I want to do is actually walk through the proofs of the last three properties, because not only will that give you some insight into the behavior of how these properties work, but it'll also allow us to practice in a more arbitrary sense how to deal with these integrals. First up, let's prove this one. The integral from a to b of f of x dx plus the integral of b to c f of x dx is equal to the integral from a to c of f of x dx. For all of these, we are simply going to invoke the fundamental theorem of calculus, do some manipulation, and get our result. So let's do this proof. All right, start at the left-hand side, and we get the integral from a to b of f of x dx plus the integral from b to c of f of x dx. Well, by invoking the fundamental theorem of calculus and letting capital F be the antiderivative of f, we get this. We get this first part, this integral from a to b of f of x dx, is equal to cap f of b minus cap f of a. That's just the fundamental theorem of calculus. And then the second integral is just capital F of c minus capital F of b. We just invoked the fundamental theorem of calculus twice. We evaluated these two definite integrals to get this sum. Now, let's rearrange some terms. Because we're just adding and subtracting, I can do that without violating any PEMDAS rules. So we have f of b minus f of a plus f of c minus f of b. And then just pull this f of c right here out in front. Get this f of b and this minus f of b together. And minus f of a, we're going to pull this to the right. So all I did was I took this and I manipulated to get this. Just adding and subtracting, so I'm not violating any rules here. But what is f of b minus f of b? So that is something minus itself. So that's equal to 0. Now we have f of c minus f of a. So we evaluated these two integrals, combined like terms, cancel some things, and we ended up with capital F of c minus capital F of a. What is capital F of c minus capital F of a? Well, by using the fundamental theorem of calculus the other direction, we get that that's equal to the integral from a to c of f of x dx. Knowing these proofs is very helpful. It allows you some intuition onto the behavior of these properties. It allows you additional practice with integrals in an arbitrary sense. It's just good practice to do these kinds of proofs. So if you have any questions about this proof, just send me an email just saying, hey, I didn't quite understand this. And then you and I will work together to make sure you come to an understanding on this one. So that's the second property. Now let's move on to this one. We want to prove that the integral from a to b of f of x dx is equal to negative the integral from b to a of f of x dx. In short, if I want to swap the limits of integration, put a negative out in front. Let's do this. Proof. Well, the integral from a to b of f of x dx, by using the fundamental theorem of calculus, that's just capital F of b minus capital F of a. Okay? But what if I want to swap those? If I want to pull a negative out in front? Well, that's just equal to negative times f of a minus f of b. Just pulled a negative out. Remember, this negative is understood to be a negative 1. So if you multiply the negative 1 back through, you end up back at f of b minus f of a. But what is f of a minus f of b? It's equal to the integral of b to a of f of x dx. Meaning, the integral from a to b of f of x dx is equal to negative integral from b to a of f of x dx. So the cost of swapping the limits of integration is just tacking on a negative out in front. Now later in section 5.5, we're going to see more examples as to why that might be useful to swap the limits of integration, but right now, just know this property. And the last one we're going to do is prove that the integral from a to a of f of x dx is equal to 0. How are we going to do this proof? You guessed it, fundamental theorem of calculus again. So the integral from a to a of f of x dx is equal to capital F of a minus capital F of a. But what is something minus itself? 0. All right, guys. So that is the Fundamental Theorem of Calculus, parts 1 and 2. Quick recap. Part 1 gives us the relationship between the antiderivative and the area under the curve, where the area under the curve is given by that infinite limit of the Riemann sums. So a remarkable theorem, a remarkable conclusion relating an antiderivative and quickly calculating an infinite limit of some summations of areas of rectangles. And then the second part, almost equally important aspect, the relationship between the derivative and the integral, and how given the correct circumstance, they actually undo each other. So it's kind of hammering home that relationship between a function and its antiderivative. If you take the derivative of something that you took the integral of, you end up back where you started. So that's the Fundamental Theorem of Calculus, guys. And then I will see you next time where we will have more fun with math.